Hello everyone. So, we have already solved analytical solution for external flows, and for internal flows for fully developed condition we could get some analytical solution. But if you have developing internal flows, then obviously it is very difficult to study, because we cannot have the analytical solution, but we can solve the governing equations numerically. So, using computational fluid dynamics technique we can solve the Navier-Stokes equations as well as the energy equation with viscous dissipation or with heat generation term in the energy equation. So, in this module we will study the solutions of Navier-Stokes equations and energy equations using numerical technique. There are three different types of discretization method: finite difference method, finite volume method and finite element method. In this course we will use finite difference method to discretize the Navier-Stokes equations and energy equation. So, in today's class we will study the basics of finite difference method. So, before studying the basics of finite difference method, let us know the classification of partial differential equations, because ultimately we are going to discretize the partial differential equations, and before using some numerical schemes it is very much needed to know the classification of these PDEs. So, knowledge of mathematical character, properties and solution of the governing equations is required. So, you can see we can classify the PDEs as physical classification and mathematical classification. In physical classification we can have equilibrium problems and marching problems, and in mathematical classification we have hyperbolic partial differential equations, parabolic partial differential equations and elliptic partial differential equations. So, first let us discuss about the equilibrium problems. Let us say that we have a domain D and this is the boundary B. So, obviously whatever partial differential equation you need to solve, you will solve inside this domain and apply the boundary condition at the boundary. Okay. So, these problems are known as boundary value problem. Okay. Like you have steady state temperature distribution. So, the equation is heat conduction equation, GAD square T is equal to 0, or incompressible inviscid flows GAD square psi is equal to 0. So, these you can see that these equations you can solve in the domain, and with proper boundary condition you can apply in the boundary. So, mathematically equilibrium problems are governed by elliptic partial differential equations. Marching problems. So, marching problems are also known as initial boundary value problems. In marching problem, so you have domain where you need to solve the partial differential equations, and at the boundary you will apply the boundary conditions, but it will march in some direction, maybe in time or maybe in space. So, if it is an unsteady problem, obviously it will march in time, and at time t is equal to 0 you need to specify the value of that variable inside the domain. So, you can see here, so this is the domain. So, governing equation at each time level we will solve in this domain, and also you will apply the boundary condition at boundary B, and you can see at t is equal to 0 you will apply the initial condition. Okay. And you will march in time or in some direction. Okay. So, differential equation must be satisfied in the domain, and boundary condition must be satisfied on boundary. So, these are tangent or tangent like problems, okay, in which the solutions in PDE is defined in any open domain subjected to a set of initial and boundary conditions. So, mathematically these problems are governed by hyperbolic or parabolic partial differential equations. So, you can have the example like unsteady heat conduction equation. So, del T by del T is equal to alpha GAD square T. So, you can see that in this case you will march in time, but if you have a boundary layer flow without separation, then you can have the boundary layer equation. Okay. So, this equation is also parabolic, and it you will march in the direction x, because at x equal to 0 you will specify the free stream velocity infinity, and in the x direction you will march. Now, let us discuss about the mathematical classification. First, let us consider a second order partial differential equation. So, consider this equation A phi x x, that means del 2 phi by del x square, plus B phi x y plus C phi y y plus D phi x plus E phi y plus F phi is equal to G. So, you can see these coefficients A, B, C, D, E, F, if these are constants or function of only x y, then this partial differential equation is called as linear equation. If these coefficients contain phi or its derivative, then the partial differential equation is called as non-linear equation, and if G is equal to 0, then this equation is homogeneous, otherwise it is non-homogeneous. So, for this equation, if you find the discriminant, so if b square minus 4ac is 0, then mathematically this equation is known as parabolic equation. B square minus 4ac, if it is less than 0, the equation is known as elliptic equation, and b square minus 4ac if it is greater than 0, then the equation is hyperbolic. Okay, so, you can have some example. So, you can have this Laplace equation, okay, heat conduction equation. So, if you find b square minus 4ac, you will find it is less than 0, then it is elliptic. 1D unsteady heat conduction equation, this is, if you find, you will get b square minus 4ac as 0. Okay. So, it is parabolic, this is equation also is parabolic, and second order wave equation is hyperbolic. Okay. So, this equation if you find b square minus 4ac, it will be greater than 0, and this equation is hyperbolic in nature. So, the detail of mathematical and physical classification you can study from any CFD book. Now, let us introduce the finite difference method. So, in finite difference method, we consider the partial differential equation, and its derivative we express in terms of its values using Taylor's series expansion. First, let us consider any function f which is a function of x. So, you can see this is the function f x, okay, and x we are plotting in x direction. If you take this variation of f, okay, with x, and at this point let us say this is the discrete point I, and this is I plus 1 with a distance delta x, and in left side if you take another discrete point I minus 1. So, this distance is also delta x, let us say delta x is uniform. Okay. So, delta x is uniform. So, everywhere delta x is same. So, now if you want to find the derivative at this point, okay, the derivative of f at this point, what you will do? Just you will draw one tangent. Okay. So, that is the exact determination of this derivative. Okay. So, this tangent will give you the del f by del x. Now, if you use 2 points to find its derivative, let us say we are using one forward point means I plus 1, at point I we want to find the derivative. So, this point and this point we are using, as we are using forward point, so it is a forward difference. So, if you join this line, then you will get a forward difference approximation. If you use one backward point, okay, so we want to find the del f by del x at this point, and we are using another point at I minus 1, which is your backward point. So, if you join these 2 points, then you will get backward approximation, and if you use one forward and one backward point, and if you join, then you will get the central approximation to find the derivative. Okay. So, finite difference representation of derivatives are derived from Taylor series expansion, and from this graph you can see that central approximation is more closer to the exact, because you see in backward and forward it is more deviated, but central is almost parallel to the exact. So, that means it gives determination of this del f by del x close to the exact solution. Now, let us consider the Taylor series and expand it. So, f x plus delta x you can write as f x plus summation of n is equal to 1 to infinity delta x to the power n by factorial n del n f by del x n. So, if you take one forward point and if you go in forward direction delta x, then you can write f x plus delta x as f x. So, if you use this expansion, then you can see plus del x del f by del x plus delta x square by factorial 2 del 2 f by del x square plus del x cube by factorial 3 del cube f by del x cube, plus it will continue. So, now if you want to find the first gradient, this derivative del f by del x, then you can write del f by del x is equal to f x plus del x minus f x, and we are dividing by this delta x. So, by delta x, and these will you take in the left hand side. So, you will get minus, so delta x square by delta x. So, you will write delta x by factorial 2 del 2 f by del x square minus del x square by factorial 3 del cube f by del x cube plus the higher order terms. So, you can see that this derivative we have expressed in terms of the discrete points using a forward point at I plus 1, that is f x plus delta x. So, the approximation using finite difference method of this derivative is f x plus delta x minus f x divided by delta x, and these higher order terms you can neglect. Okay. So, these terms are known as truncation error. Okay. Truncation error. Okay. So, if you see, if delta x is very small, then delta x, okay, will be larger than delta x square, and delta x cube will be much smaller than delta x square. So, anyway you can neglect the higher order terms, and this is whatever you are actually neglecting, that is your truncation error. So, what is the definition of truncation error? You can see from this expression that truncation error is the difference between the partial differential equation and the finite difference approximation. If you see the order of x in the leading term of truncation error, and that is known as order of accuracy. So, if you can see in this truncation error, the leading term is this one, and here the order of x is delta x. So, its order of accuracy is delta x, and it is first order accurate approximation. Okay. Similarly, now if you use one backward point and if you use f x minus delta x, then you can write from the Taylor series expansion as f x minus delta x del f by del x plus delta x square by factorial 2 del 2 f by del x square minus delta x cube by factorial 3 del cube f by del x cube plus higher order term. So, now if you want to approximate this gradient del f by del x using one backward point, then you can write f x minus delta x, and you divide by delta x, then this term will become delta x by factorial 2 del 2 f by del x square minus delta x square by factorial 3 del cube f by del x cube. So, you can see the finite difference approximation of this del f by del x is f x minus delta x divided by delta x. So, you have represented this del f by del x using two discrete points f x and f x minus delta x, and this is your truncation error, and in the leading order term the order of delta x. So, this is order of delta x. Okay. So, order of delta x is 1. So, its order of accuracy is order of delta x. Now, let us consider the derivative of t with respect to x, okay, and the discrete points are I j, I plus 1 j and I minus 1 j. So, let us consider these points I j, I plus 1 j and I minus 1 j, and you have a uniform grid. So, the step size is delta x, and we want to find the derivative del T by del x, where T is the temperature. So, you can use the Taylor series expansion. So, you can write T I plus 1 j is equal to T I j plus. So, you can see this is I plus 1 j has a distance delta x from I j. So, you can write delta x del T by del x at point I j plus delta x square by factorial 2 del 2 T by del x square, okay, at I j plus delta x cube by factorial 3 del cube T by del x cube, and we are not writing the other higher order terms. So, if you want to find the derivative del T by del x at I j, so you can rearrange and write del T by del x I j is equal to T I plus 1 j minus T I j divided by delta x minus delta x by factorial 2 del 2 T by del x square I j plus delta x square, it will be minus by factorial 3 del cube T by del x cube and other higher order terms. So, you can see your del T by del x. So, you can represent using forward point T I plus 1 j and T I j. So, what will be the order of accuracy? So, if you neglect this truncation error, then order of accuracy is delta x. So, it is a first order accurate discretization, and it is known as first order forward difference approximation, because we are using one forward point, okay, and order of accuracy is first order. And you can see the distance between T I plus 1 j and T I j is delta x. So, T I plus 1 j minus T I j by delta x. So, it is the finite difference approximation of the first gradient del T by del x at point I j. Now, similarly, if you consider one backward point I minus 1 j, then you can find the derivative of T with respect to x as, so you use Taylor series expansion T I minus 1 j. So, we are using one backward point. So, you can express in terms of T I j minus delta x del T by del x at I j plus delta x square by factorial 2 del 2 T by del x square minus del x cube by factorial 3 del cube T by del x cube at I j and other terms. Okay. So, now if you want to represent this first gradient, then you can rearrange it and you can write T I j minus T I minus 1 j divided by delta x, and you can write minus plus delta x by factorial 2 del 2 T by del x square and minus delta x square by factorial 3 del cube T by del x cube I j and so on. So, you can write del T by del x in terms of 2 points T I j minus T I minus 1 j divided by delta x. So, you can see this is the finite difference approximation of this first gradient using one backward point, and order of accuracy is delta x. So, this is known as first order backward difference approximation. Okay. Now, use one backward and one forward points and find the approximation of this first derivative del T by del x and the second derivative del 2 T by del x square. So, using Taylor series expansion, you can write T I plus 1 j as T I j plus delta x del t by del x plus delta x square by factorial 2 del 2 t by del x square plus delta x cube by factorial 3 del cube t by del x cube and del x 4 by factorial 4 del cube del 4 t by del x 4 I j and other term, and t I minus 1 j you can write as t I j. So, here minus delta x is there, then wherever delta x is there you put minus delta x, then you will get this expansion So, in this case you can see that we are putting delta x is equal to minus delta x. Okay. So, we are writing the Taylor series expansion. So, you can have the higher order terms. So, what you do? So, you first subtract the second one from the first equation. Okay. So, we want to find the del t by del x. So, if you subtract the second equation from the first. Okay. So, if you subtract, what you will get? You can see you will get left hand side t I plus 1 j minus t I minus 1 j is equal to. So, if you subtract, this will get cancelled, here you will get 2 delta x del t by del x at I j. If you subtract, it will get cancelled, here you will get 2 delta x cube by factorial 3 del cube t by del x cube, okay, and this will also get cancelled and other terms. So, now if you write the approximation of first derivative del t by del x. So, you can see it will be t I plus 1 j minus t I minus 1 j divided by 2 delta x, and you will get minus. So, 2 will get cancelled, it will be delta x square by factorial 3 del cube t by del x cube and other higher order terms. So, you can write del t by del x as t I plus 1 j minus t I minus 1 j divided by 2 delta x, and what is the order of accuracy? You can see it will be delta x square. So, it is a second order accurate. So, it is second order central difference approximation, because we are using one forward and one backward point, and we are finding the derivative at I j, and you can see these 2 points are separated by a distance 2 delta x. So, del t by del x we are writing t I plus 1 j minus t I minus 1 j divided by 2 delta x, and order of accuracy is second order. Now, you add these two equations. So, and find the second derivative of t. So, if you add okay. So, if you add it, you will get, so 2 t I j, this term will get cancelled, then you will get 2 delta x square by 2, factorial 2 is 2 del 2 t by del x square, then you are adding. So, this will get cancelled, then you will get 2 delta x 4 by factorial 4 del 4 t by del x 4 I j, okay, and other higher order terms. So, now you can see you can represent this second derivative using 3 points t I plus 1 j, this if you take in the left hand side you will get minus 2 I j plus t I minus 1 j divided by delta x square. Okay. delta x square, and you will have minus 2 delta x square you are dividing. So, it will be delta x square by factorial 4 del 4 t by del x 4 I j and so on. So, you see the finite difference approximation of this second derivative about point I j as t I plus 1 j minus 2 t I j plus t I minus 1 j divided by delta x square, and what is the order of accuracy? It is second order. Okay. So, generally whatever equations we will consider, we will have first derivative and second derivative. You can see that in Navier-Stokes equations as well as in the energy equations, you will get the first derivative of temperature and the second derivative of this temperature. So, we have derived del 2 t by del x square. So, similar way you can write del 2 t by del y square as t I j plus 1 minus 2 t I j plus t I j minus 1 divided by delta y square, because in y direction you are taking the derivative del 2 t by del y square, that is why you are dividing by delta y square, and its order of accuracy will be second order. Now, we have learned how to use the Taylor series expansion to find the first derivative and second derivative. Now, let us consider steady state heat conduction equation and discretize using finite difference method. So, you can see we have this equation, 2 dimensional steady state heat conduction equation. These are the discrete points. So, this is known as grid. So, we will discretize this equation about this point I j. So, you have I plus 1 j, I minus 1 j, these are the index, okay, and I j plus 1 and I j minus 1. We have a uniform grid delta x in the x direction and in y direction delta y. So, delta x may not be same as delta y, and grid aspect ratio we are defining beta as delta x by delta y. So, del 2 t by del x square, if you use the second order central difference approximation, then you can write t I minus 1 j plus minus 2 t I j plus t I plus 1 j divided by delta x square, and similarly t I j plus 1 minus 2 t I j plus t I j minus 1 divided by delta y square is equal to 0. If you rearrange it, you can write t I plus 1 j minus 2 t I j plus t I minus 1 j plus delta x square by delta y square, we are writing beta square t I j plus 1 minus 2 t I j plus t I j minus 1 is equal to 0. So, this equation is your discretized equation. Okay. So, this is your algebraic equation. So, that we have discretized about this point I j. So, this is the equation we have written for this I j. So, you can write similar equation for each point. So, you will get a system of algebraic equations. Okay. So, once you get the system of algebraic equation at each point, then you need to solve using some iterative method. Now, let us consider 2 dimensional unsteady heat conduction equation. So, this is the unsteady heat conduction equation with your heat generation term, okay, and we will use explicit approach, that means there will be one unknown. So, we will use forward time discretization. So, now we need to march in the direction of time. So, we will march in time from n to n plus 1. So, n is your previous time, okay, and this is your current time or present time. Okay. So, we are just marching in time from n to n plus 1. So, this derivative now we are using forward time. So, t I j n plus 1 minus t I j n divided by delta t, and this already we have discretized using the central difference, and alpha is the thermal diffusivity, plus you have the source term which is your heat generation term q triple prime by rho into C. So, now you can write, you can see here you have one unknown term n plus 1 and all are at time level n. So, you can express t I j n plus 1 in terms of the known terms. So, you can see alpha delta t by delta x square t I minus 1 j n plus t I plus 1 j n plus alpha delta t by delta y square into t I j plus 1 n plus t I j minus 1 n plus for the t I j coefficients, if you get together, you will get 1 minus 2 alpha delta t by delta x square minus 2 alpha delta t by delta y square plus q triple prime delta t by rho C. So, this is your equation, and it is you see you have only one unknown and all are known from the previous time level, and this is known as explicit approach, but limitation of using the time is you will get from the stability criteria, and here delta t you have to choose from this stability requirement. Okay. So, delta t should be less than equal to 1 by 2 alpha into 1 by delta x square plus 1 by delta y square. So, obviously you can see if you refine the grid, then delta x delta y will be smaller, and accordingly you have to decrease the time step delta t, and when you are going from n to n plus 1. So, this is the time step delta t. Now, we will use backward time, and in that you will get more than one unknown, and you will get a system of linear algebraic equations, and this method is known as implicit method. So, the same equation we are considering, 2 dimensional unsteady heat conduction equation. Now, if you discretize using first order, this is your T I j n plus 1 minus T I j n divided by delta t, and all these terms you write in terms of current time level n plus 1. Okay. So, all we are writing at n plus 1 and plus the source term. So, if you rearrange it, so you will get in the left hand side we have written all unknown terms, you see n plus 1, and in the right hand side T I j n is known, and the source term is also known from the known heat generation per unit volume term. Okay. So, this you can see this if you write the system of equations, you will get a pentadiagonal matrix. So, that you need to solve using some method, and the advantage of this implicit method is that it is unconditionally stable. Okay. If you do the von Neumann stability analysis, you will get it is a unconditionally stable. So, what is the order of accuracy of this discretization? So, the order of accuracy for this explicit method and implicit method is order of delta t, because it is first order accurate in time and second order accurate in space, delta x square and delta y square, because you can see this is order of delta x square, this is the order of delta y square, and this is the order of delta t. So, this is the order of accuracy of this method. Using the finite difference discretization method, we have converted the partial differential equation to system of algebraic equations. So, that you need to solve at each discrete point. Okay. So, there are many iterative methods are there. So, one is direct methods are very time consuming. So, direct methods like Cramer's rule, Gauss elimination or LU decomposition. So, generally these are not used in CFD. In iterative methods you have Jacobi method, Gauss-Seidel method and successive over-election method. So, these are mostly point by point method, and also nowadays you can use some advanced iterative method like conjugate gradient or biconjugate gradient method, and using these iterative methods you need to solve those algebraic equations. So, you can see iterative methods are said to be converged if the error epsilon is less than the convergence criteria. So, you have to set the convergence criteria, let us say 10 to the power minus 6 or 10 to the power minus 5, and this epsilon you need to calculate from the value of the discrete point. So, at each point if you have T I j at k plus 1 either iteration level or time level minus T I j k whole square, and you sum it up for all the grid points. So, I is equal to 2, j is equal to 2 to I is equal to m minus 1, j is equal to n minus 1, where m and n are the total number of grid points in x direction and y direction, and divided by total number of grid points m minus 2 into n minus 2, and you take the square root of it, then you find the epsilon. This epsilon if it decreases with time, and when it will go below the given convergence criteria, let us say 10 to the minus 6, then your iteration will stop. Now, we will discuss about the variable storage. Say when you are solving Navier-Stokes equations and the energy equation, how many variables you have? You have velocity u, v, w in 3 dimensions, and temperature, and you have pressure P, because pressure is appearing in momentum equations. Okay. So, obviously, you have total 5 unknowns, okay, 3 velocities, pressure and temperature. So, where will you store or where will you solve these variables? So, depending on the storage variable storage, we can have staggered grid and collocated grid. So, first let us discuss about the collocated grid or non-staggered grid. So, you can see you can divide the domain into discrete points. So, that is known as grid, and these are the grid points, and in each grid point if you solve all the variables, okay, in 2 dimension you solve u, v, pressure, temperature or any other species, okay, like mass fraction. Okay. So, if you solve at same grid point, okay, then this is known as collocated grid. Okay. So, all the variables you are solving at the same point, but it is having some disadvantage. Okay. So, that is known as pressure velocity decoupling. Okay. So, when you are solving the Navier-Stokes equation and energy equation, you will get pressure velocity decoupling. That means pressure and velocity will not talk each other. So, if you see here the let us say this is the pressure distribution. Okay. So, you have a discrete points, and at discrete points you have the pressure distribution 100, 200, 100 and 200. So, for some physical situation it may arise that your pressure is varying like this. Now, at this point if you want to find the pressure gradient using collocated grid for the Navier-Stokes equation, then you will find del P by del x. So, del P by del x is the if you use central difference, you can see 100 minus 100 divided by 2 delta x. So, it will become 0. So, you can see pressure gradient is 0, but pressure gradient is the driving force for the velocity, but here pressure gradient is becoming 0. So, that is known as pressure velocity decoupling. So, you can see for a checkerboard kind of pressure distribution or velocity distribution in collocated grid, velocity fields with checkerboard pattern would be seen by discrete continuity equation as uniform flow field, and pressure fields with checkerboard pattern would be seen by momentum equation as uniform field, because it seems like a uniform field. So, that you do not have the pressure gradient, but you have pressure gradient, but it is varying. So, similarly continuity equation, you see if you apply del u by del x here, it will become 0. So, it will feel that it is a you have a uniform flow field, but you have a velocity variation. So, that is the disadvantage of collocated grid, but you have some way to overcome this problem, and you can use momentum interpolation like Rie and Cho proposed the momentum interpolation. So, that you can use to overcome this velocity pressure decoupling problem. Another grid is staggered grid. So, in the staggered grid, the velocities are solved in staggered grid point. Okay. So, you can see here. So, this is the grid. So, if you see this is the grid point. In staggered grid, pressure and temperature or any other scalar like mass fraction, these are solved at this main grid point, but velocities are solved in a staggered point. So, here velocity u is solved and here velocity v is solved. So, this is the velocity u and this is the velocity v, and at these points pressure is solved and any other scalar like temperature are solved. So, you can see velocities are solved in staggered way, that is why it is not it is known as staggered grid, and this pressure velocity decoupling is avoided using this staggered grid, and that is why in staggered grid you will get strong coupling between pressure and velocities. Okay. So, you can see in the staggered grid you have pressure at this black dot, velocity u in this red dot, and v velocity you will have in these blue dots. But here you can see you have some problem in bookkeeping. So, for pressure you can see you have interior points 1, 2, 3, 4. Okay. And if you consider the boundary points, then here you have one boundary point, here another boundary point, so you have 5. But when you are considering u, so in x direction how many points are there including the boundary points? 1, 2, 3, 4, 5, and in y direction if you consider the boundary points, so 1, 2, 3, 4, 5, 6. Okay. If you consider v in x direction, if you consider a boundary point 1, 2, 3, 4, 5, 6, but in y direction 1, 2, 3, 4, 5, and for pressure in x direction 1, 2, 3, 4, 5, 6, and in y direction 1, 2, 3, 4, 5, 6 including the boundary points. So, you can see you have total number of points for solving the velocities u v are different in x and y direction, and it is also different than the p. So, this bookkeeping is the difficult in staggered grid, but you need to be careful while solving these velocities and pressure, and accordingly you need to solve for the interior grid points. Okay. So, that you need to be very careful while solving the equations using staggered grid, but the main advantage of staggered grid that you can avoid this pressure velocity decoupling, and obviously you will get a strong coupling between pressure and velocity. So, in today's class we have introduced the partial differential equation, and we have discussed about different classification of partial differential equation, physical classification and mathematical classification. In mathematical classification we have elliptic equations, parabolic equations and hyperbolic equations, and in physical classification you have equilibrium problems and marching problems. So, in equilibrium problems are mostly governed by elliptic equations, and marching problems are generally governed by parabolic and hyperbolic equations. Then we have introduced the finite difference approximation using the Taylor series expansion. We have used a forward point and backward point, and we have written the expression for the first derivative, and also using central difference we have written the approximation of the first derivative and second derivative. So, you can see the forward difference approximation and backward difference approximation, the order of accuracy is 1. So, that is the order of delta x, but when you use central difference method, then order of accuracy is 2, because order of delta x square. Then we discretize the partial differential equation of steady state heat conduction equation and unsteady heat conduction equation. So, after discretizing you have seen that you will get a system of algebraic equations, and you need to use a suitable iterative method to solve this system of algebraic equations. Okay, because at each grid point if you write that equation, then you will get a system of algebraic equations. And for explicit method you will have only one unknown, but delta t has the restriction due to the stability criteria, but in most of the time in unsteady two dimensional heat conduction equation we have seen that this implicit method is unconditionally stable. Then we have discussed about the variable storage. Depending on that we have classified the grid as staggered grid and collocated grid. In collocated grid all the variables are stored at the same point, but it is having the problem of velocity and pressure decoupling. To avoid that problem you can use staggered grid, where pressure and any scalar like temperature and species is stored at the main grid point, and velocities u v are stored in a staggered manner. So, in the staggered grid you will get a strong coupling between pressure and velocity. Thank you.